Hey guys, my name is Jeffrey, and my two lab mates are Jennifer and Tien, and we're going to be talking about our research project, the development of an open source satellite design toolkit. We worked with our PI, John Huang, and mentor Victor Gandarillas in order to design this toolkit that will optimize the design and performance of small satellites. And this toolkit will contribute directly to our lab's larger project called VISORS, which is a space mission that seeks to design and launch two CubeSats into low Earth orbit. And they're going to be transmitting data from the sun back to Earth.
Yeah, so essentially our research aims to answer the abnormality with the sun's temperature distribution. While the sun's temperature should typically decrease as the distance from the core increases, there's a sharp spike in temperature at the sun's corona, which is the outermost part of the sun. This is what's being displayed in figure 1 if you see. As you approach the corona region, the temperature spikes by orders of magnitude, and we don't really know why. Due to many technological limitations that prevent scientists from accurately modeling the corona's environment, this phenomenon has baffled them for decades. To answer this question, as Jeffrey mentioned, two independent CubeSats will line up for a brief period of time in their orbit. They would essentially form a virtual telescope and transmit data about the coronal structures in the sun's atmosphere back to Earth for review, and hopefully find an answer. Our part, more specifically, however, focuses on the design optimization for the CubeSat, with each of us focusing on a specific design element: thermal, attitude, and the battery subsystem.
Okay, so for the steps we took to start, all of us had to set up the environment. And so to do that, we had to obtain the necessary operating systems, tools, and packages. And so this would basically include installing Linux, Visual Studio Code, OM tools, OpenMDAO, Python, and Miniconda. And once our environment was set up, all of us could begin modeling our assigned disciplines by creating Python scripts within Visual Studio Code, using OM tools to declare components and model equations, debugging our code, and using N2 diagrams to visually check the equations we've modeled, and then pushing our changes to GitHub, where we would share the changes we've made with each other. And so figure 3 is basically a flowchart of the general steps we took to model each of our respective disciplines.
Yeah, and one of the other tools we needed to use for our tasks is something called the Surrogate Modeling Toolbox, or SMT for short. SMT is an open source Python package, which consists of surrogate modeling methods. And for those that don't know, a surrogate model is an engineering method used when an outcome of interest it cannot be easily directly measured. And in our case, in order to model the battery components, we'll be taking experimental data in order to create a surrogate model that will represent the behavior of the battery cells as a function of state of charge and temperature. And in figure 4, you'll actually see one of the types of batteries we'll be using to model the behavior of.
So essentially, SMT, or the surrogate modeling toolbox, as Jeffrey mentioned, was also utilized to generate equations from physical data for the thermal subsystem. In this type of work, there are often very few equations governing the desired effect that we're looking for. As Jeffrey mentioned, there's no state of change as a function of temperature or the effect of temperature on solar panel efficiency that we can easily look up and plug in numbers. So we had to create our own. Once we had our surrogate model, we combined them with existing thermal equations to create a comprehensive view of our system. These equations are then implemented into OM tools to generate a model representing the physical thermal limitations of the CubeSat.
Okay, so for results for the attitude discipline, we were able to create a model that is able to compute the external torques acting on the CubeSat due to the reaction wheels. And so in figure 5, what you see here is basically a sample of the code that was worked on.
And for the battery model, so we knew that the simplest circuit model that would be useful for us is an RC circuit. And since the battery itself is not an RC circuit, we used experimental data to model the behavior through SMT. And as a result, we were able to successfully create surrogate models for the predicted behavior of internal resistance and open circuit voltage versus the state of charge. And in figure 6, we'll actually see that through some data points, SMT was able to create the predicted data shown by the yellow line for the behavior of internal resistance at different state of charges, which turned out to be one of the easier models because it was nearly linear. And even though the battery discipline's main focus was on the surrogate models, we also created a model for the battery cell in order to approximate the transient effects and the behavior of the battery cell as a circuit.
For the thermal model, a heat conduction in the solar panel is created from existing thermal equations as well as surrogate models. The model determines the limiting temperature and safe temperature range derived from the interactions between many essential subsystems, like the battery, communication, and avionics. If you look at figure 8, it's just a small snippet of the code that was also utilized to help generate the model.
So so for the additive discipline, because the model we built was able to calculate external torques acting on the CubeSat, researchers could use this model to help determine the satellite's attitude or their orientation in space. And so that would be very useful because they can use it to help maneuver the two CubeSats from its observation phase when it's observing and collecting data on the sun's corona to their charging phase, where basically they're no longer observing the sun's corona and they're basically conserving or recharging themselves for the next time.
And in figure 9, we see what we call an N2 diagram, which essentially shows all the relationships of the different components and subsystems in the models that we created in this lab. And although hard to see, the tabs on the left show all the different parts and variables. And if we were to hover over the boxes forming the upper triangular shape, it would show arrows that would indicate the relationships associated with the chosen component. And we use this diagram in order to check if we've accurately modeled our desired discipline, whether it be attitude, thermal, or battery. And because of this, in particular, the battery models were made and will help the visors team determine efficient power and current draw for the different hardware components on board the CubeSat, such as the comm system, the actuators, and valves.
So the thermal model is a crucial consideration that couples many disciplines. Not only does it affect solar power generation and battery performance, it also includes heat transfer from avionics and communications. More importantly, however, the thermal model depicts the limitations that dictate critical components of the mission or parts that could result in failure if not properly modeled.
So to summarize, for this project, we coded models for the satellite's attitude, battery, and thermal disciplines in Python using an existing open MDAO framework, and then incorporating it into the new framework, OM tools. And so this is important because the open source toolbox that we're contributing to will set a precedent for the design and optimization of any future small satellites, not just the CubeSat. And so the next step in this research is to expand the toolbox to account for more disciplines such as propulsions, orbital mechanics, and communications.
And lastly, we would like to acknowledge the GEAR program and everyone at GEAR for giving us this opportunity to pursue this research. We would also like to acknowledge our PI, John Huang, and the LSDO lab for giving us all the resources to do our research. And we would like to acknowledge our mentor, Victor, for just guiding us through the entire process and helping us as much as he could.